to this piece of paper that we signed, you guys signed up. First of all, are there any people who have not signed up in this sheet? Okay, good. I will pass this around. First, for those who haven't signed up, to please sign up. And second, those of you who are here will therefore hear the second announcement. So only those who are on this sheet and are not here today need an email from me to send to tell them that we are moving Monday lectures. I would therefore ask you, even those who have signed up, to next to your name put a check mark or an X to indicate that you were here today. I'm not actually checking if people are here, I don't care. But just for today, because those of you who are here, I will not need to send an email to everybody else who is on this sheet but hasn't checked the name. I will then send an email. Make sense? Okay, good. So please check next to your name or sign up if you haven't, and then put the check next to your name, obviously. The homework number 1 will be posted Monday, this coming Monday. It will be due a week later. It will cover everything we've said last lecture, everything we'll say this lecture, maybe a little bit from Monday's lecture. That's why we are posting it on Monday. And as you can see here, Monday lectures have been moved to TBM at the other side of campus, lecture room B. I have no clue where it is. And the irony is that by asking to move, and they moving us over there, essentially we will reduce the number of people showing up on Mondays, because nobody in their right mind will go from here to TBM just for this lecture, or not nobody, but quite a few wouldn't. As a result, I would expect the number of people will be lower anyway, but still, just to play it safe, because we had the trouble last Monday, the room didn't fit everybody. We now have a bigger room at the other side of campus. Any questions on any of this, please? Is there also a time for the deadline? Yeah, that will be posted. Usually it's 5 p.m. of that day, and it's not 5:01. Those of you who know me from other courses, it's 5 p.m. Okay, so we are continuing our discussion on classical laminated plate theory. And last time we essentially finished by simplifying a lot of things. And instead of using stresses, we use integrals of the stresses, or integrals of the stresses times the z through the thickness coordinate, which gives us moments. So we have the so-called stress resultants, which are the 3 forces per unit width, x, y, and xy being the shear force, and then the 3 moments per unit width. The sign convention is as shown here, and that's the one everybody should please try to be using. With this in mind, to just show a direct and obvious, but still to reinforce an obvious relationship, if I have a certain force, this is units of force now applied, if I divide that force by the cross-sectional area, width times h, the height, I get obviously the average applied stress. And this average applied stress is then, by definition, the 1 over the thickness times the integral of the actual point-wise stress. And because this, we just said, here is the nx force per unit width, we can then arrive at this relationship, which, even though obvious, many people tend to forget, and it can be quite useful many times. So we then said, okay, we have this equation 1,1 that we introduced, and I will show that again in just a second. And we also introduced the mid-plane strains, 2 normal strains and 1 shear strain, mid-plane of the laminate that we are dealing with. And we said if we take this equation 1,1, so let me fly back, which is here, this equation 1,1 relates stresses in the coordinate system 1,2, which is not necessarily aligned with the fibers in any ply, to strains in the same coordinate system through these coefficients that we defined and even calculated a little bit last time. So if I take, let's say, the first one, and I integrate through the thickness, I will arrive at the relationship shown here at the bottom, where the nx, because that's the integral of the stress through the thickness, relates to the three strains via three elastic properties, which are three entries in the so-called A matrix, and they are membrane properties because they refer to only in-plane performance of the structure. If I have an applied force, I get, in general, three strains in my laminate. If I have an applied strain or three strains applied, I end up with in-plane forces. One important characteristic for a composite, notice the presence of this term. Basically, I can apply a axial force and get a shear strain, or I can apply a shear strain and get an axial force. Not for every laminate, but in general for laminates for which this term A16 or this integral here is non-zero, that would be true. In metals, you cannot have that. You cannot have a uniaxial load and cause shear strain. So if I did it for the other two equations relating stresses and strains, I would get two more equations that in matrix form gives us the so-called membrane behavior, where the in-plane forces are related to the in-plane strains. And the A's are given as integrals of these QIJs, the QIJs being the stiffnesses. And because through the thickness each of the QIJ is constant, I can replace the integration with summation throughout all plies, as long as I calculate correctly the integral dz, which is just the z coordinate at the top of the ply in question, which is the kth ply, minus the z coordinate at the bottom of that ply. What that means, to repeat and reinforce a little bit, is that if I have a laminate if I define z equals 0 here, let's say, that becomes now my z0, and as I integrate through the thickness, I can determine the course for each ply. I will have a zk at the top and a zk minus 1 at the bottom of each ply, which are the coordinates with respect to my origin. And that gives me every single term in the A matrix. That's the end of last lecture. Just to recap and also to create an analogy with what we're about to say now, which is the bending behavior or out-of-plane behavior. Now, in general, for any structure that we will be dealing with, it suffices to assume that the strains through the thickness are linear. Basically, they consist of a constant term which represents the strain in the mid-plane and a linear distribution of strain, linear being linear in z, z being the out-of-plane coordinate, and the constant of multiplication here, or constant of proportionality, happens to be the 1 over the radius of curvature. That's just standard mechanics for basic plane stress type of deformation out of plane. So the strain now at any location through the thickness is therefore a linear function, and if I replace my second derivatives shown here with a common symbol kappa x, kappa y, kappa xy, which are the three curvatures, I can write in a more concise way the same thing. So this is the general case where I can have both stretching and bending, and just simplify things, let's say I only have pure bending. Pure bending means that there's no stretching. Remember our Bernoulli-Euler beam types of assumptions. If I have no stretching of the mid-plane, then the three mid-plane strains are 0. And by integrating now, again, those 1-1 equations, so I'm flying back, see how fast I can find it. So these equations are still valid, but now we will replace the strain with its linear dependence, and we will integrate this relationship through the thickness, provided we multiply by z also. It appears arbitrarily we multiply with things, but the only reason we do this is because we want to refer everything to the force resultants nx, ny, nxy, and the moment resultants. And we know that the moment resultants are integrals of stresses times the out-of-plane coordinate. So I basically take that first relationship of those equations and I multiply by z and integrate, and we would get this plus additional terms. I forgot to say plus here, additional terms. But this is the strain now. Epsilon, whoops, where am I? Z times this second derivative with a minus sign is the epsilon x strain, which is shown right there. So this is the mx by definition. And in the general case, when we have the epsilon x, the epsilon y, and the gamma, the kappa x, kappa y, and the kappa xy, we will generate the general relationship which involves q11, q12, q16. The 2 here comes from the fact that our curvature relationship here for this twisting strains involves this factor of 2. So I can then, for pure bending, say that the curvature, the radius of curvature, which is essentially this second derivative, is 1 over the radius of curvature in the x, and then 1 over the radius of curvature in the y direction, and then this one is a weird combined radius of curvature that I have no feel physically what it is, but it's there. The bottom line is those will be constant for pure bending, because we're saying that basically the radius of curvature is locally constant. That means I can take them out of the integrals. So this second derivative here becomes a kappa x with a minus sign. It's lumped in here. Kappa y here and kappa xy, and I'm left with these integrals, which again, same way we did for the in-plane behavior, can be integrated throughout the thickness. And because throughout the thickness each of the q's, which are stiffnesses, are constant, we can make them into summations, and the z dependence becomes this integration of z squared, shown here at the top right, which becomes z cubed at the top surface minus z cubed at the bottom surface. So we can then call these conveniently d11, d12, d16, and therefore in general, if we only have pure bending, the moments per unit width are related to those curvatures, or kappa x, kappa y, and kappa xy through this matrix. And you might wonder why all of a sudden we started with A and we jumped to D. There's a B, but there's no C, for reasons that I hopefully will remember to tell you in just a second. As if this were not enough, composites have coupling or exhibit coupling performance in general. Basically, you can have in-plane load, and as we said, you can have shearing as a result of it, which is a mild case of coupling, stretching, shearing, coupling. What makes things worse is you can have an in-plane load and generate an out-of-plane bending, or can have a pure bending moment applied and generate in-plane loads. And the way to see that is, again, if we go back to this same equation that relates stresses to strains, but now include the in-plane and the out-of-plane dependence, and we integrate with respect to z directly instead of multiplying by z and integrating. So we take the basic relationship, integrate with respect to z, which means this integral of sigma x will become our nx, the force in the x direction of the laminate. And then the q11 integration will become the a11 we saw just a little while ago, the a12 and the a16, which are lumped here. And then the remaining are new quantities, which are now the q's times the integral of z dz instead of q times the integral of z squared dz or q dz. So this new integral is now our B matrix, so that's where the B comes from. And we have, as a result, the coupling matrix that tells us by how much the structure would bend if we were applying an in-plane load, assuming it's a composite structure. And therefore, we have the overall relationships. If we put them together in matrix form, we have the forces, nx, ny, nxy, and the moments, which basically are related to the mid-plane strains and the corresponding curvatures. Now, for a given loading situation, the mid-plane strains and curvatures are supposed to be constant. So Once you know the loading, you can find the curvatures, or once you know the curvatures and the midplane strains, you can find the loading. Notice, of course, this is a pretty ugly-looking matrix. There is the A part, which relates directly in-plane properties in terms of loads to in-plane strains. There's the D part here, which relates just the bending with the curvatures, and then the B matrix will couple in-plane loads with out-of-plane curvatures or in-plane strains with out-of-plane bending loads. So in general, this is all there, which is quite unfortunate because it complicates things. So this is the A, the D, and the B, and there is no C because C in general is either the compliance matrix or a stiffness matrix, depending on how you formulate things, and people had been using C for a very long time before the composite theory had been formulated, and they decided they did not want to create a confusion, so they jumped from B to D instead of from B to C. That's the main reason. Two important characteristics of certain types, certain classes of laminates. If I have a symmetric laminate, then the B matrix is 0. Symmetric means that with respect to my mid-plane, which in this case with my 4 laminates is just 2 layers above and 2 layers below, with respect to this mid-plane, a certain ply, which has an orientation theta, let's say, will have a corresponding one at exactly the same mirror image location, which has exactly the same orientation. So with respect to the mid-plane, this would be a symmetric laminate because the theta 1 at the top ply is the same as the bottom one, and the theta 2 at the mid-plane or the ply next to mid-plane is equal to the one right below the mid-plane. Once you have this, you can basically show that if you go to our B matrix definition, so I'm jumping back for a second here, you can show that these terms will cancel out because whatever you get above the mid-plane as a contribution will be cancelled by whatever you get from below the mid-plane. As a result, the B matrix is 0, which simplifies things. That's one case. The other case is the terms that relate in-plane load with a shear strain or in-plane shear with an axial strain there. Those A16 and A26 are 0 if for each plus theta, which can be anywhere in the Steitting sequence, there is a minus theta anywhere in the Steitting sequence. They don't have to be next to each other. They don't have to be in the symmetric locations. As long as for every plus theta you have a minus, then you are fine. And as a result, A16, A26 is 0, which means you cannot couple the in-plane stretching behavior with the shearing behavior. Now, as a nice add-on is the question, okay, if you look at my D matrix, the D16 and D26 terms, what they do is they couple torsion or twisting with bending. So if I have pure bending, actually the structure will also twist, or the other way around, if I have pure twisting, the structure also bends. So for this not to happen, so this type of coupling not to be present, we need D16 and D26 equals 0. So can anybody tell me, either from previous knowledge or very quick thinking, what types of laminates have D16 equals D26 equals 0? Gentlemen there? Okay, I'll give you that. Good. Any other case? Okay, that's also true. Excellent. Now, suppose you have some plus thetas and minus thetas. Can you create a laminate? Everything you said is perfectly correct. There's one more general case. Excellent, yes. So anti-symmetric. So if at a certain location I have a plus theta and the corresponding location with respect to the midplane I have a minus theta, and that is valid for all the plus thetas and with the minus thetas, then all the D16 and D26 terms will cancel out because the contribution above and below the midplane cancel. That's very good. Now, in general, we are not given the strains, but we are given applied loads. So if you looked at the relationship we had before, it was relating forces to strains and curvatures, and that's not the most convenient way. This is much more convenient because typically we're given forces and moments, and we need to calculate strains and curvatures just because that's very useful for calculating failure eventually. So all you do is you go back to your linear algebra and you take this huge matrix and you invert it. Or you ask MATLAB to do it, and I invite you to try to do that with a good size laminate, not 090, but something complicated. In most cases, it can't invert it. Not that it's not doable, it's just that numerically it becomes quite difficult. I've had a student doing that in general, and it just was a nightmare. And of course, you cannot have symbolic manipulation to do it. Maple, it's a 6 by 6 matrix. You get 60 pages for each term if you get that. It turns out, of course, the people that originally developed this method, they recognized that because of the symmetries that, let me go back up. Because of the symmetries present, if you look at each of these segments, it's self-symmetric. B12, B12, B16, B16, B26, B26 shown here, and so on for the D and the A matrix. You can use that and a lot of knowledge and time in your hands, and actually you can invert them. So the alpha matrix, which is at the top left, shown here now at the bottom, is given by this mess, which involves the inverse of the A matrix. So the exponent -1 here refers to inverse of a matrix, and a quite complex term here that involves, again, inverse of the A matrix and a whole bunch of terms that make up this new matrix, the inverse of which you have to take, and so on. Similarly, the beta matrix, which is the top right or the bottom left, will consist of this, and finally the delta matrix. Now, if you look at different textbooks, you may find, and typically you will find, different expressions for these. They all lead to the same thing, because depending on how you do this inversion, quadrant by quadrant, if you will, you can write these expressions slightly differently. So don't be surprised. Just make sure when, for example, if you need them in your homework, you might need them, you stay consistent with whatever equations you chose, because if you program half of the equations with one expression and the other half with another, they may not be consistent. You have to stay consistent with one set of expressions. Now, if the laminate is symmetric, we said the B matrix, the capital B, or the coupling matrix, is 0. And when you invert it, then the inverted matrix will also have a beta matrix equal to 0. So it ends up being in this form. And then instead of using the alpha matrix, we call it the little A matrix and the little D matrix. The reason is that in the general case, they are not the same. But if the laminate is symmetric, then they would be the same. So we created this construction, which theoretically appears reasonably interesting, but it has to have some relationship with reality. And so far, the only relationship with reality was when we said that force divided by cross-sectional area gives me the average stress, which I can relate to Nx. So all I have said so far is that somehow, in an obvious way, the loads relate to the average loads that we defined per unit width. But that is not even close to an attempt to design an actual laminate and come up with failure predictions. And to start with that, we have to think, what do we typically get in the laboratory as actual measurements? And the first thing that you know is that if I load something in tension and somehow I measure the stress, F divided by WH, my average stress, and the mid-plane strain, I would get, if all is well and the material is well behaved, a straight line, the slope of which is the Young's modulus, and that's fine. We are making some assumptions here. We are saying the laminate is not unsymmetric. The laminate is symmetric, so the coupling situation is pushed aside for now, just to make a point. So in the laboratory, we measure Poisson's ratios and shear modulus or Young's modulus, and everything we said here would be essentially useless if we could not relate our A, B, and D matrix with actual useful quantities. So let's see how this comes about. Let's take a symmetric laminate which is under uniaxial tension, which means Nx is the only load applied, and Y and Xy are 0. And if you look at relationship 1,6, which let's find where that is, so that at least, yes, okay, 1,6. Basically, we say it's symmetric, so the B matrix disappears. So I have Nx is A11 epsilon x0 plus A12 epsilon y0 plus A16 gamma xy0. That would be the general. And these now times those are not there because the B matrix is 0. Similarly, the ny would be coming from the second row times that column. So if I go back, the first equation is A11 epsilon x0 plus A12 epsilon y0, and I'm neglecting the A16 gamma xy0 just to make the algebra a little easier. You can include it, and the final answer will have many more terms, but just to show the process. If it's under uniaxial tension, Ny is 0. So from the second equation, I can solve for epsilon y0, and what I get is I get this, which I can now substitute to the first equation where epsilon y0 is to get nx is A11 epsilon x0 minus A12 over A22 times another A12 that we have over there. So that's A12 squared epsilon x0. So if I factor out my epsilon x0, I arrive at the equation here in the middle that relates the nx with the epsilon x0. But we said before that there's a relationship between the average stress and nx such that essentially my force, instead of just saying it, we said, where is it? That sigma 0 is nx over h, and sigma 0 is also f over wh. So this is what we invoke here. And yes, we can move. Which will tell us that if I substitute for nx in terms of sigma 0, which is f over wh, I will get 1 over h, basically the stress. This relates nx, but nx is f over h. F over w. F over w is nx. So if I want to calculate sigma 0, I take my f over w and divide by h. But my f over w, which is nx, is given by this. So the right-hand side here has the f over w and the 1 over h coming from this term. So now I have finally managed to relate my applied stress to the resulting strain. And we know that stress and strain related through a constant coefficient means that that constant coefficient is the Young's modulus. So this thing is not cooperating. So my Young's modulus for this laminate is given by this quantity, which involves directly the A matrix. And you can also show that the quantity here in brackets is actually the 1 over little a11. So the inverse of the A matrix involves this little a11 term. And you might say, how do you know? Let's see if I can remember my matrix manipulation. So I have my A matrix is A11, A12, 0, for the case of a balanced laminate. So if I want to invert this, let's see. Let me move here to the right. Now I claim, because this is a symmetric matrix, the inverse of this will have this term to be 1 over A66. The zeros will stay where they are. And then all I have to do is invert this guy. And to invert this guy, I need to calculate the determinant, which is the determinant of the 2 by 2 only, A11, A22 minus A12 squared. And then I take this term and put it there. So it's A22 delta. This is minus A12 divided by determinant. I'm sorry, let's not call it delta because it gets confused with a discriminant. And then it's symmetric, minus A12 over the determinant and A22 over the determinant. Now I know that these days you just ask Maple to do it for you, but to at least convince you that this might be the correct one. That means now this term here is my little A11, because by definition we said the inverse of the A matrix is the little A matrix. So A11 is A22 over this determinant, which hopefully is the same as I wrote there. A11 is A22 divided by this determinant here. So I can either write my stiffness in terms of the capital A matrix or in terms of the little a matrix, which is what most people do. So stress relates to strain through this coefficient of proportionality, which is my stiffness 1m. 1m is important, even though you can use any symbols you like. 1 is the direction in which this is acting. So for our laminate there, it would correspond to a load applied in this direction and a strain measured in that same direction. Then the stiffness that we would get, or the Young's modulus we would get, would be that one. And this is not the same as the stiffness in any other direction in the laminate. So that's why we have to differentiate, or at least indicate in what direction. There's also a subscript m, which is for membrane, which means that this is for in-plane loads and pure in-plane strains. Because if you bend the structure, the Young's modulus you would measure is not necessarily the same as we are about to see. So far with me? Okay. So the same way that we did this for the one direction, you can do it for the two direction, and you will see the analogy directly. And for the G12, which is the shear modulus for in-plane shearing of that laminate. And then you have the two Poisson's ratios. This is loading in one direction and measuring the transverse contraction in the two direction. And the bottom left here is loading in the two direction and measuring the transverse contraction. Make sure you keep in mind that these two Poisson's ratios, nu12m and nu21m, are not necessarily the same. In general, they will not be the same. Now, this is the left column on this page. The right column said, well, what if instead of having pure stretching, you would have pure bending? So you would get different expressions, which now involve the D matrix, the little D matrix shown here at the denominators. And those will very rarely be the same as the membrane ones. So it's important to keep that in mind. We will see that again in much more detail when we talk about buckling of beams and so on. But there's a membrane set of stiffness values and a bending set of stiffness values, and they are in general different. And you have to decide in advance which are the ones that are operative for your problem and use the correct ones, or if you don't know for sure, use the ones that would give you conservative results. We will see cases later on where it's actually not even obvious what you should use, and it's up to you. Some people use the average, some people use, or most people use the most conservative. So this, ironically, is the end of, ironically in the sense that we did it very quickly because it's supposed to be a review of the classical laminated plate theory. So to do your homework, you need to know all this and have a program that does most of this. And eventually for the course, you need a program that will do all of this. We'll talk about software on Monday briefly. Let's talk now about failure, because everything we said tells us how to determine stiffnesses, how to determine strains given loads. So, okay, once you got your strains and your stresses potentially, how do you relate those to the strength of the structure, and how do you predict failure? So one method is what's called the use of first ply failure criteria, or open parentheses for the non-Greeks in the audience. The word in singular is criterion, coming from the Greek word criterion, and in plural is criteria, which is many of them. So this means there's many criteria or many ways of predicting failure, as we're about to see. So being Greek myself, I do have a little bit of a partiality on this term being used correctly. Not that I will take off points unless you do it too many times, and then my patience is exhausted. What you see here is the 787 wing box after the test. And you see the failure here, which is very close, I think, to the butt line 0, or the very main center of it. I'm not sure exactly where it is. They always make it a point, Boeing and Airbus, to take photographs that are very difficult to deduce where you are in the structure, what type of structure you are dealing with, and even what the loading was. And we'll do some of that at the beginning of the next period, try to play a little bit the spies and see if we can deduce some interesting things. This being the 787, now if you look closely here, you will see that where it broke, it actually has moved up. Moving up means it was actually under compression. So that means most likely that this wing box was doing a maximum upbending, which would put compression on the upper skin, assuming this is the upper skin and they did not turn it upside down and they're trying to fool us that way, but let's make some assumptions being engineers and see how far we can go. So maximum upbending, and this broke here, and you will see that they're fairly massive. The thickness is fairly high here. Thickness is fairly high means you have a lot of plies, because the plies that make up a laminate are typically 0.15 millimeters. So this may have 100 layers here at the thickest, or 200. I should remember Monday to bring you some examples of really thick composites. It is natural to assume, and in fact tests show that if you apply a load in such a thick structure, the final collapse or complete destruction, as shown here, is not the same as the onset of failure. As you apply load, you will get something to start failing, which usually is referred to as first ply failure. Basically, there will be a ply somewhere in this stack-up that will break in a certain way. That doesn't mean that you have final failure. And that immediately brings up a major problem that we have when we do failure predictions in composites. Even if you knew how to predict that first ply failure, how does that relate, if at all, to the final failure, which is what you are primarily interested in? Keep that in mind. We'll come back to this. Failure, as a rule, starts at the weakest link. It sort of makes sense, but if you compare it with what happens with stiffness, then it's actually quite insightful to think about it. If you're trying to calculate stiffness where you use a multiple set of materials, you will calculate the corresponding stiffness of each material and end up with the total stiffness as a weighted average of all the stiffnesses. For example, we said that for the A matrix, Aij is summation of Qij times the Zk minus Zk minus 1 term, which means for a certain stiffness in a certain direction, let's say the 1, 1 direction, you take the stiffness of each ply in that direction and multiplied by this. This now becomes a weighting factor. It so happens if all the plies have the same thickness, this term would be exactly the same, but not all the plies will have the same thickness in a general design if you use different materials. So there's a weighting factor, and this then makes it some kind of a weighted expression. So in stiffness, everything contributes and somehow will be put together. In strength, the weakest link is what starts everything, and it has nothing to do with how strong you are in other locations. And the weakest link in general, if you think in terms of the constituents, which are the fiber and the matrix, is the matrix itself, unless you are using metal matrices, which are extremely expensive and not commonly used. But let's say we are dealing with composite materials where the matrix is typical resin of today, which would be extremely weak compared to the fiber. So that's what will fail first. And as you can imagine, if it's not a very strange stacking sequence, then that failure does not mean that the fibers, all the fibers around that failure will fail. So load gets transferred from the matrix that broke to adjacent fibers through matrix that's still intact, or even through the broken matrix, and you can still carry load. And in fact, you can move load away from the plies whose matrix has failed to other plies, and then behave as if you had absolutely no knowledge of that local failure. Going back to a picture we saw before, this is these are zero plies, so the fibers are running as from left to right in the middle, and these are minus 45 plies, and the little dots, essentially, those white speckles, spots are just the fibers coming towards us at an angle of 45 degrees. So this is a crack at the top left here into the matrix, which basically occurs in between fibers. Similarly, this is a crack here. Now, that happens very early. If you imagine a tensile load being applied, it happens very early because the matrix is weak. And even if I break this here, all that means is somehow I take the load that was into this bottom right portion, transfer it through the very stiff fibers here, and bring it back into the structure or the ply behind this crack. And you can do the same thing here, unless cases where you have delaminations, which means you cannot take load from here to here now because they have separated. So the mechanisms are there, and I'm trying to indicate that there's multiple mechanisms, and what happens first is not necessarily what relates even to what happens last. Or if it does, it's a fairly complex process going from one failure mode to the next. When the fibers break, of course, it's much more interesting, and you can see here that we have a whole bunch, the thickness of the laminate is in this direction, up or down, and all the plies have completely failed, and there's also some delaminations. So that's the ultimate goal, predict what's on the right, but we will start with trying to predict what's on the left, and we'll sort of stop there because we will simply raise our hands up and admit complete defeat. So let's get into the failure modes of a ply in 15 minutes. That way we'll maintain the momentum. This is close enough to 15 minutes, minus half a minute. One correction, when I was writing the inverse of the A matrix, I had the A22 here and A22 there. This A22 is correct. This one was wrong. It should say A11. That's an oversight, thanks to the gentleman that pointed that out. Now, before we continue, we'll actually play, as I was saying, spies or detectives, composite detectives. I mean, imagine your business, your job is being a composite detective. But it can be interesting. Where's my chart? There it is. So back in December, Airbus did the ultimate load test of their wing. And watch the picture. I mean, can you give me any information, man? Or are you, whoops, hang on. Are you just, if I even enlarge it, right? So what do we see? We see, if we use our imagination, that there's a fuselage here. These are the cockpit windows, so it's coming at us. And this is actually the one wing and the other wing. And this is the so-called wiffle tree, which is the scaffolding that applies all the loads. And talk about not giving any information. It's a picture which could be like my son playing with his mechano thing, and with the proper coloring, it could easily have been that. But the fact remains that they actually did it. And let's read a little bit because it's interesting. The company states it has applied up to 1.5 times higher than those the aircraft or the loads. Successfully performed the ultimate load test. The company states it has applied loads up to 1.5 times higher than those the aircraft would ever encounter in its entire in-service life. This is public relations at its best. I mean, everybody knows this is the ultimate load. It's a requirement. You don't just do it because you are conservative. You are told by law you have to apply 1.5. But if you write it this way, it's a wonderful way of bringing in a sense of security, because people say, okay, they actually multiply by 1.5. Now, they forget that if you get in an elevator, the safety factors there are 8. They actually multiply by 8, but the weight is not an issue. But, and if they thought about that there are some people that are afraid getting into elevators, if you told them it's a safety factor of 8 and you're still afraid, what would you do if the safety factor is 1.5? I think that will increase the number of people that are afraid in getting in airplanes by a lot, including my wife. I haven't told her that. Wingtip deflection exceeds 5 meters. Okay, that sounds phenomenal, but if I tell you now it's 32 meters per wing, so it's 64 approximately total. So I have, where's my chalk? Basically 5 divided by 32 is the tangent of the angle, right? So if this is my wing and it's cantilevered here, yes, I know it's actually bends, but well, let's do it bending so the purists among you don't complain. So the wing does this, and this is 5 meters, and this is 30, what did I say, 32. So if it were straight, which would mean it would even be a bigger angle, you know, this angle here would be the tangent is 5 divided by 32, which is 0.15. No, I don't just do tangents in the back of my mind. I have done it, and hopefully I remember correctly when I did it. This one, which translates to approximately 8 to 9 degrees. So you have a beam which it's fairly sizable and only has a angle here that's, or this angle here is 8 to 9 degrees. Why am I saying all this? So is this a linear theory or a non-linear theory? Is this large deflections or not? I think it isn't. The point is, knowing your beam theory now and knowing this size and this and that angle, you can take nonlinear beam theory, which involves elliptic integrals if you're so inclined, or just the standard forget-me-not equations that we've done the good old days, assuming some kind of a constant lift distribution, but calculate the EI, or an average EI. You can calculate the average EI for this, and knowing the average EI, you can then make a statement about how thick is the skin, because you have to reproduce that EI given a certain geometry, and the core depth is approximately known. If you look into Wikipedia, you can find that. So you can actually do that game, and you say, okay, you reach certain conclusions. Airbus, we'll continue on this in a bit. Airbus explains it already passed the last of the ultimate load tests for the fuselage, so that's great. Basically, they are done with the ultimate static testing. And of course, here's the story about they analyze. The huge volume of data is analyzed and correlated to the structural computer models. You know, this is just, I have a finite element model, and I take all my strain gauge data or other type of data, and I have to show that they match. If they don't, I have a problem. Remember this, the company states it has applied loads up to 1.5 times higher than those the aircraft would ever encounter in its entire service life. Now let's see how the 787 announcement was when they first came out with the same story. First of all, look at the picture. Do you see any similarities? It's a completely different company, each at its other's throats. They would kill for a useful picture, but they both know how to give you a useless picture. Here's the exact same thing. The 787 cockpit, the wing, bending like crazy, and all the scaffolding so you cannot see anything. And I mean, I don't blame them. I would probably do the same thing, but it just makes it harder for us to try to deduce a few things. So now remember what we were reading. This was back in March 28th of a couple of years ago. Today completed the ultimate load wing upbending test. At least here they give us a little more information. It's upbending. I mean, you can tell by looking at it, but at least they say it. On the 787 Dreamliner, during the testing, loads were applied to the airframe to replicate 150% of the most extreme forces the airplane is ever expected to experience while in service. Makes you suspect that the PR person, the public relations person, is the same. They just changed companies, and they said, this is what we'll give to those guys. It's the exact same framework. Give them a feeling of this being a very good piece of work, which it is, a very safe piece of work, which it is, but don't tell them, okay, this is legal. By law, they have to satisfy this. It's just because it sounds so good to know that there's a safety factor of 1.5. The wings were flexed upward by approximately 7.6 meters. Now, this is interesting because the wing is shorter. Remember, the 787 is slightly smaller. So I would have 7 divided by 30, which would make the angle bigger. And you can sort of tell by looking at the picture now that this is really bending up. And of course, this may not be at ultimate load, maybe more than ultimate load. They never tell us. But the point is the angle would be bigger, so I would expect the 787 to be more flexible, so the EI that one would back calculate would be smaller, and that would make some interesting thinking in terms of, okay, flexible wings have certain aerodynamic properties that are desirable, but also their dynamic properties might not be. So it would be interesting to carry this further, and every once in a while we'll be doing some of this, not necessarily on the same topic, because it can take 3 months, and then we would be off by a factor of 2 in the end if we don't have all the information. But that is where we are. As of December, the 787 has passed the full-scale tests, and if I can find my correct file. Yes. We can continue. Failure in composites. We said that, didn't we? Yes. So, a single ply can fail in at least 5 different ways. Remember, a ply is just one layer with fibers in one direction, at least for unidirectional tape material. So the first type of failure is tension along the fibers. Now, tension along the fibers might mean a lot of things. It might mean that you actually start pulling the fibers away from the matrix if the matrix bond to the fiber is not strong enough, or you can simply be breaking fibers. And that's just the beginning. Once you start breaking fibers, you have huge stress concentrations at the location where the fibers broke, which means most likely that the matrix now will fail there. So the sequencing of events becomes quite critical after a while. So that's what it looks like. My fibers are horizontally at this picture. The applied load is in tension. Now, you could have tension perpendicular to the fibers, which is this picture at the bottom left, with the fibers again running horizontally. In this case, no matter how you slice it, unless you have fibers in the loading direction, it's the matrix that fails first. Given the fact that it's much weaker, it will fail first. Then you can have the exact same things, but now you reverse and you have compression. This is where it starts getting a little problematic. Yes, I can have compression along the fibers, and yes, I can cause failure. But locally, what happened is not necessarily a pure compression failure. We'll briefly talk about this some more. Usually what that means is locally, because the fibers are not perfectly straight and because they buckle locally, it's like a beam on an elastic foundation, the elastic foundation being the matrix, they actually move out of plane, out of their axis, away from the axis, and that causes shearing loads, and that's what really probably drives failure, or at least starts failure in these cases. And you can have the compression perpendicular, which is the exact reverse of what the bottom left is what we have now in the bottom right. And again, it's mostly a matrix-driven failure, which might eventually break the fibers themselves. And finally, the fifth one is the shear, which is actually a shear failure in the sense that matrix fails in shear first and then triggers failure of the fibers. So in principle, even though each of these 5 types of failure might involve, at a lower scale, a completely different type of failure if you go into considering what the fiber does individually and what the matrix does individually. If you somehow lump what happens into these 5 failure modes, then you can start talking about a way to predict when a ply fails, and then if you know when a ply fails, maybe try to predict when a laminate fails. But from the question here, I am going to say it's not necessarily the right approach, but it's one of the best approaches we have. And as long as you use it with caution and with lots of test results to support your predictions, then you are fine. So you test for these 5 failure modes. So that becomes a series of tests. Each of those gives you a value here. Each of these tests will give you a value. And somehow this value now relates to, or can be used to relate to, final prediction of failure. And in general, because there are 5 different modes, somehow they will interact, so you need a criterion or a method to put them together, and that's what's called a failure criterion. That's what we will end up doing, but let's say we recognize at this point that this is not very accurate because, as I mentioned, what happens at the local matrix and fiber level or scale can be quite complex and might be different than what we think at the ply level. You could alternatively start at the individual fiber and matrix level. And this becomes a PhD student's dream and an engineer's nightmare because the results look great, but they hardly correlate with tests unless you are extremely careful. If I have a laminate, or a ply, single ply, a single layer with fibers, let's say, in this direction, and I apply a tensile load. Now, the fibers do not all have the same strength. In addition, there are local defects. There are some fibers which have surface scratches or cracks, or the bond with the matrix is not strong enough, or the distribution of fibers is not even enough. So you end up having a lot of matrix or a lot of fibers in one location versus another. In the end, no matter how you look at it, one fiber will break first. But that in and of itself doesn't mean much, because you can show analytically, and tests support this, that all that means is you have a zero stress at the bottom here of this top part of the fiber, or at the top of the other half, and that within a very short distance away from that cut or crack, the matrix will transfer by shear all the load back to that fiber. So a single cracked fiber means nothing really, and other than locally you have a stress concentration which increases the load in the adjacent fibers. Now if those adjacent fibers happen to be weak enough, you can break those, and if you are unlucky enough to have a whole bunch of fibers next to the broken fiber that are very weak, then you can actually trigger final failure by breaking everything through the stress concentrations that are created. In general, that's not the case, because randomly, if you look at it, simply you will transfer the load from this cut. The shear stress in the matrix now, if I start from this point and go up, so this is that fiber here, is shown here next on this plot. The shear stress is 0 here, but it increases to a very high value because it tries to transfer all this load that was originally here, and then comes down to 0 because at the same time the load in the fiber starts from 0 and increases to the far field value some distance away, which by the way is about, should say here, about 10 fiber diameters. It takes about 10 fiber diameters to appear as if there's no crack, because if the load in the broken fiber is back to its full strength within 10 fiber diameters, then only within those 10 fiber diameters something serious is happening. So I broke one fiber, and unless all the fibers around it are very weak, then that's no big deal, until that same fiber, if it happens to be weak throughout its length, then breaks in different locations. And okay, I broke it enough times that the matrix now is running out of space to be able to transfer the stress from one break to the remaining fiber, or it runs out of strength because all this keeps increasing the, there's a stress concentration effect that keeps increasing the stress in the matrix itself. So which fiber breaks first is completely random, because we don't know out of the billions of fibers which one is the weakest. Where does it break, and how is the load on the adjacent fibers affected? That's where it becomes an interesting problem in analytical modeling, and people have been working on this over the years and still working. I even have a student doing a master's thesis on this right now. How many breaks before the fiber is ineffective? That depends on the strength of the adjacent fibers. But you can see easily how complex it can get simply by trying to track failure from one location of a fiber to the next one and determining what's the load between fibers and along the fibers. That was just the tension case. If I now do the compression case, well, I don't. I find a student by the name of Wout de Bakker, and I tell him, okay, you do the compression case for me, and he does a master's thesis on this. What happens is, if you think about the individual constituents, fiber and matrix, then the failure possibilities or the failure modes are quite different than tension and quite different than a pure strength kind of failure. In a metal, if you do compression, locally there is some shear and the metal yields, that's it. In a composite, you can have what's called fiber kinking. Fiber kinking is shown here. Nominally, the fibers are straight, but locally, they won't be perfectly straight. And even if they were, under compression load, they actually start bending out of shape. It's like a local buckling-driven kind of phenomenon over a very short wavelength. And in the end, they develop this kink. Straight here, straight back here, and then there's the so-called kink band, or a location where all the fibers have been twisted enough to the side, and you can see them here from a scanning electron microscope, and they actually break. So that's one possibility, which may or may not happen depending on the type of fiber, depending on how well this ply has been constructed in terms of how straight it is and so on. The other possibility, which is more common, is that you can have fibers wavy, even though you expect them and nominally they are straight. If you look at a small enough piece of the composite or of the ply, you will see that they are wavy, and there are the two theoretical possibilities, which are the in-phase case, basically all the fibers are in phase, or the out-of-phase case, which they are 180 degrees out of phase, or of course the reality, which is a mix, and we don't do the reality because it's too difficult unless you do a Monte Carlo simulation. Now, applying compression in these guys means that the waviness will increase. Basically, the fibers try to shorten, but because they are already bending out of shape, they will bend more. As they bend more, they develop higher bending stresses. So the combination between the compression stress and the bending stress will eventually cause this to fail. Well, we admit defeat until my student finishes his work, then maybe we can have better results. And we go back to the ply properties that we said we can measure, even though those mask or hide the real local failure phenomena. And we call tension X with a T parallel to the fibers, X with a C in compression, and then the Y's are the transverse direction corresponding tensile and compressive strengths, and S is our shear. Important for these names because they show up in all kinds of failure criteria. There are very many failure criteria. In fact, President Lincoln said you can have a, well, nothing, didn't talk about criterion, but to paraphrase what he said, you can have a failure criterion that works for some cases all the time, or for all cases some of the time, but you cannot have a criterion that works for all cases all the time, and that's a fact. In fact, I will show you some more quotes as we go. The easiest criterion is the so-called maximum stress criterion, which is very similar to the yield, the Tresca yield criterion, I think, in metals. You basically determine the stresses parallel to the fibers. So in this case, the subscript X denotes parallel to the fibers. And you compare it to the XT value here. So if the stress in a ply exceeds this value, obviously then it has to fail. That seems reasonably obvious. And similarly, if the X, sigma X parallel to the fibers is compressive, instead of using this value, you would use that value. Experimentally, those are quite different, and that's important. In metals, the tensile yield and compressive yield for most alloys of aluminum, let's say, are reasonably close, within a few percent. Here, they can be off by more than 30%. Similarly, if you have loading in the Y direction, then Y direction being perpendicular to the fibers, then you would use the tensile or compressive strength perpendicular to the fibers. And again, if the applied stress exceeds the allowable strength of the material, then you have failure. And finally, you would have the shear. I put the absolute value because whether it's positive or negative, you just take its absolute value and compare it to the measured shear strength. And if it exceeds, then you are in trouble. Now, you can logically think that if I only have one single stress, let's say sigma X were the only one applied, this criterion makes perfect sense. And in fact, it works very well if you have only one single stress. But if you have a combined state of stress in a ply, then it's not at all obvious that it suffices to compare the stress parallel to the fiber to the corresponding strength. And if it doesn't fail, you say, no, okay, I have no failure. And then the sigma Y to its corresponding strength value and so on. That's where combining the stresses becomes important. If you think physically, suppose I have failure in the matrix because of tension in the matrix. If I have shear, that doesn't mean that the matrix cannot carry any shear now, because essentially I have these cracks in the matrix which are simply shearing, and yes, they are moving around as I apply the shear load, but that doesn't mean they cannot take some load. So obviously, a single failure according to this criterion does not mean I have correctly predicted failure if I have a multiple state of stress, multiple state of stress in that ply. The complete counterpart, instead of using stresses, using strains, is shown here. So basically you compare strains to their corresponding strain allowables. Now if you had a perfectly linear system, so there is no, the stress-strain curve is completely linear, then the two criteria would only differ by the Poisson's ratio effect between stress and strain. Please.
The stress that you're looking here is a combination of matrix and the fibers, or only fibers? Or?
It's the ply stress. That's a good question, whether the stress is the combination of matrix and fibers or just individual. It's the ply level stress, which means you have already translated fibers and matrix into a single ply with the stiffness matrix ABD matrix, and you are calculating the corresponding stresses and strains for the entire ply. It's not on the fiber level or on the matrix level alone. So there's a maximum strain criterion, or then it starts getting interesting. People are saying, instead of using the individual ones, I recognize that somehow they combine either destructively and they cause earlier failure, or constructively and they delay failure. So Steve Tsai, now retired, a very famous person, not only for the criteria that he came up with, took a theory by a gentleman called Hill, which was developed for metals, for anisotropic metals. There was a yield theory that he developed, and he said, I will take that theory and translate it over to composites, which was the first big mistake he made, not in terms of being wrong, but in terms of exposing himself to a lot of criticism. We'll talk about criticism a lot. In the sense, if you are the first one to do something, if you do it perfectly, then everybody uses what you did. If you do it very well, but there you leave room for criticism, then a lot of people will criticize, and we'll see the criticisms as we go. What he said is, if I try to take the limiting case of a composite becoming a metal, I want whatever expression I will derive for a failure criterion to, in the limiting case, give me the behavior of that metal. Now, physically, that has absolutely no reason why it should happen, because the mechanisms of failure in composites are different, and therefore there's no reason why. But it's a very nice way of trying to encapsulate both metal and composite behavior. So it turns out, if you put them in this form, again, the sigma x, sigma y, tau xy are the applied stresses on your ply at the ply level, and x's and y's and s's are the corresponding tensile or compressive stresses depending on the sign of those applied stresses in the ply. So if this left-hand side is greater than 1, you have failure, because it means that at least enough of these numerators are greater than the denominators, and therefore the applied stresses are greater than the strengths. Then there was a generalization that Steve Tsai and Ed Wu did, which said, okay, this really doesn't recognize the fact that I can have different tension strength and compression strength in a composite, while, as I said, in metals, those tend to be close enough that you can use a single value. So let me now introduce the XT and XC, which are the individual tension and compression values, and the YT and YC for transverse, and the S value here. Now this criterion becomes this one. And in fact, there's a whole mathematical derivation that derives this and makes sure that this criterion, if you had an isotropic material, would give you the yield, the von Mises yield criterion. Again, arbitrarily was chosen by these gentlemen, Steve Tsai and Ed Wu, to do it so that there's a limiting case recovered by that criterion, and that was one of the main reasons there was a lot of criticism. Parenthesis, Ed Wu was unfortunately, he passed away, a brilliant guy that used to work for the US Air Force. And if you work for the US Air Force, unfortunately or fortunately, you also have to teach pilots, and pilots are not necessarily inclined in learning composites. So the story goes, and I have it from a sure source, that he would basically cut deals with the pilots to take him up on their F-16s and their F-14, F-14 is Navy, whatever the Air Force, F-18 maybe. They take him up and for a ride, and then he would help them a little bit on passing the courses. But he was a brilliant gentleman, and we'll come back to him if I remember as we go. I need to introduce another gentleman in a little bit. If I have pure tension, I can show that most criteria, and this is an example here, will give me about the same predictions. So this is my angle theta for a laminate that's 0 to theta 2 minus theta 2 symmetric. The reason this laminate is selected is because it has very peculiar failure behavior. And the gentleman working with me these days has actually created this, which shows the failure load on the y-axis as a function of the theta location, as predicted with 3 different criteria: Puck, the maximum stress we just saw, and the Hoffman criterion. And interestingly, in most cases, the predictions have nothing to do with what happens in reality. Even though the criteria seem to agree, in reality, the minus theta applies no, the plus state applies will develop a crack, a matrix crack first, which is a transverse failure. Then you get a delamination between the plus theta and the minus theta, which none of these criteria can predict, and then you get final failure. So this is to show that even though the criteria agree with each other reasonably well, they might not be close to what the actual specimens would do. And recognizing this problem, many people have tried to compare actual test data, shown here, with different criteria. And this is a gentleman called Edge from England, John Hart-Smith, which is a guy I need to introduce right now, and Puck, which is probably the best criterion we have today. And you will see that they differ quite significantly in some locations in the envelope. And in some cases, they are unconservative, as at the bottom left here. In others, they are quite conservative. John Hart-Smith, a brilliant gentleman from New Zealand, who used to work for Douglas Corporation, McDonnell Douglas, actually became a fellow. Fellow for these companies means that you are recognized as a worldwide authority in what you do, and he was very good at composites. In fact, he developed the best, for quite a while, for decades, the best methods for joint analysis of bonded joints and bolted joints, among other things. He's the kind of guy who over the phone could solve a problem. You would tell him, I have this kind of sandwich, and he would tell you, without you having enough time, based on the loads, what the thicknesses should be for this to work. He's also responsible for the so-called 10% rule, and we'll talk about the 10% rule a lot in this course, so just in the back of your mind, keep that in mind, but that's John Hart-Smith. Then when Boeing bought McDonnell Douglas, he became a Boeing fellow, and he has now retired, living in New Zealand. He was the first one to openly, aggressively criticize this approach of coming up with failure criteria that look mathematically elegant, but capture very little of the physics. And I will show you what he thought in a little bit. And he attacked, sorry, going back, he mainly attacked Steve Tsai or Tsai and Hu for their criterion or the criteria of this type. That brings me to the other story I wanted to say, which is in a conference years ago in the early 90s, there was this big hotel in Lake Tahoe, and there were the people going for the conference who were interested in the conference and the papers being presented. Ed Wu was there. And the people who were going there because they wanted to go on vacation, had nothing to do with the conference. So for those people, there were all kinds of electronic games. And one of the games at the time, which was very popular, you had this big screen. We're talking 1991, so it was this huge screen, and you had a gun. You are like a Western cowboy, and you would be seeing the streets of a city, and a city of, you know, a saloon and a bar and everything, and you would be walking through, and different people would be attacking you, and you had to shoot them down, and of course not all of them were the bad guys. So Ed Wu was seen holding that, and every time he was shooting, he would say, Hart-Smith, Hart-Smith, Hart-Smith. He was pretending to be shooting Hart-Smith, but he was a very nice guy. Both of them are. So the stresses or strains in this criteria are parallel and perpendicular to the fibers in each ply. That's important if you're doing a failure prediction using this criteria, and you will be doing that for homework 1. You take the applied load, you translate it to strains. From those strains, you calculate the ply level strains, and then you relate those to stresses. Those are stresses in the original coordinate system of the laminate, and you have to rotate. All that is explained also in the textbook in case you are not familiar. But so if my original X and Y coordinates is like this, and these are my plies, I have some kind of loading. Let's say I have a bending moment being applied. This translates to strains through the thickness in this coordinate system. And those strains I can relate now to stresses for each ply in this coordinate system. But if, let's say, for this top ply, my fibers are at an angle to this coordinate system, I have to rotate the stresses I calculated in this coordinate system to the local coordinate system. We saw everything about stress transformation last time. Pretend this is perpendicular to that. So in the 1-2 coordinate system, and then you take those stresses and you put in these criteria. So if you take the laminate stresses, then you get useless results. they only predict failure of that specific ply in that specific failure mode. For example, if I'm saying this is my, not this one because it's difficult, if I'm saying sigma x exceeds xt, all I can say is that I have failure of the fibers in tension for that ply. Do I have final failure for the entire laminate? I don't know. That's all I can say. So it can be very conservative because it only predicts onset of failure, first ply failure. Hence the name first ply failure criteria. They cannot predict in principle final failure. What you have to do now is you have to say, okay, the load that was in the ply that failed has to somehow be carried by other plies. You make an assumption, logical assumption, how that's carried by the other ply, and you can go into post first ply failure criteria or progressive failure. And people have done that with mixed results. It doesn't work with a simple approach that says, for example, if the matrix fails, I set the transverse properties of the ply that failed to 0. That won't give you final failure in the end, except for some simple laminates. Everything we said is in plane, and unfortunately composite will fail out of plane because the matrix that connects the layers between them is very weak, and we need special criteria which have been again developed, but they require determination of the stresses out of plane, or they require fracture mechanics with energy release rate calculations. Given all this mess, in 1982, my professor, when I was a student, a master's student, Professor Lagasse, said or wrote, there are as many failure criteria as there are researchers in the field. I think the latest count is more than 70 failure criteria. And the consensus has yet to be reached. That was in 1982. Now, he also developed his own criterion, quite useful for out-of-plane failure. So if you are into this field, you'd better have your own criteria at some point. So 30 years later, in 2014, we are pretty much at the same situation. We have approaching 100 failure criteria, none of them working well enough. And in fact, scientists all over the world or researchers got together and they did the so-called worldwide failure exercises, and you can look into that into the internet. This is now at its third attempt. There was the first worldwide failure exercise, the second one. I think they're doing the third one now, and we still haven't found a good enough criterion. Zvi Hashin, I think now retired in Israel, a very famous also professor working on the topic, known for the Hashin criterion, said that he was asked about failure criteria and his opinion, and in fact his own criterion, and he said, my only work on this subject relates to failure criteria of unidirectional fiber composites, so it's not even with multiple orientations, not to laminates. I must say to you that I personally do not know how to predict the failure of a laminate, and furthermore that I do not believe that anybody does. So what are we doing here? And you actually have a homework for starting Monday. Well, we have to live with reality. I mentioned the gentleman, John Hart Smith, who is the main attacker of the Sai-Ru criteria. Look at this. This is actual publications, and if you are as famous and as smart, you can get away with this. The relevance of most composite failure criteria to conventional fiber polymer composites is claimed to have remained undetected. Basically, he's saying the composites fail in a completely different way than these criteria imply. Then the Sai-Hill failure criterion. Nothing in Hill's work addresses more than one mode of failure, and he should therefore be spared the ignominy, this is a New Zealander speaking, of association with the many abstract mathematical failure theories for composite materials. Yet, in the UK and Europe, Sai's misinterpretation of Hill's theory of anisotropic plasticity is referred to as the modified Hill theory. And it should now be evident that the innumerable abstract mathematical failure theories are, it is clear then that the unstated simplifying assumptions of traditional composite failure theories are so contradictory to basic laws of physics that the theory should be discarded. That's why he came up with two failure criteria, which themselves don't work perfectly well, but they are physics-based, at least make an attempt. As a message to you, if I don't poke my eye out, as a message to you, the best criteria we have now that seem to work in many more cases than others is the PAC criterion and the LARC3. The LARC3 is much more complicated, but it's based on the PAC criterion. LARC3 means Langley Research Center. 3 is the third version. There's also a LARC4. In fact, I know the guy that developed this with some colleagues. my message also to you is keep that in the back of your mind. So if you talk to a purist and they start telling you this criterion is not good, you know where they're coming from. But you still have to generate a prediction today for your structure that's going to be flying tomorrow. And you need something to get started, to decide how many plies to put together, and then basically to decide what to test. So use whatever you like. I recommend any version of the maximum stress, maximum strain, or my personal favorite, which is the one that's been attacked the most, the Sai-Wu criterion. Those I have programmed into my computer, and those are the ones to check your results. But if you use a different one, that's fine. Any legitimate criterion, legitimate. Don't come up. If you come up with your own, better have a good explanation. If you convince me, I will accept it. If you don't, then you lose a lot of points. So let's switch now to the real course. This was all the review. So you're supposed to know all this stuff. Where's my glasses? So we'll start by, now we've done failure, sort of. We've done stiffness properties, classical laminated plate theory. Let's now start thinking about real structures and what we need to predict how real structures behave. Yes, I'm sure most of you know, but so I'm going a bit quickly. A typical airframe will consist of all kinds of members, each of which has a special purpose. There are beams, shown here, the longitudinal beams on the floor. There are stringers on the skin. There are skins that are not shown so we can see through. Bulkheads, which are just glorified frames. There are fittings, and so on, each of which has a purpose, and each of which has to be analyzed, each of which has to be first designed. So let's take a real scenario here. This is real life now. To design a whole aircraft, you have to take it through all the possible maneuvers. It has to make turns at different radii, at different rates, accelerations. It has to do climbs and dives. It has to even crash and so on. You have taxi, crash, then the flight maneuvers, and then all these are static and fatigue versions, which ends up being a list of about 2,000. It's at least 1,000 if you do it right, about 2,000 maneuvers. So that means that 2,000 load cases. And let's say at each location in your aircraft, you have at least three different design concepts. For example, if you're doing skins, you can have the so-called stiffened skin with skin and stiffeners, or a sandwich, both of which we will cover in this course. Or you can have the so-called grid stiffened structure, where you have these tiny grid that actually stiffens your structure and gives you strength. Three alternatives. Now, for each of those, you may have three different ways to make it. For example, if it's skin with stringers, you can co-cure, which means both of them go together, and then you go in the autoclave and cure, and out comes the perfect structure. Or you can cure them separately and then use fasteners to hold them together, which is more like the black aluminum old method of doing things. Or you can use adhesive. This color here is meant to be adhesive between the two. So I have three alternative designs, three different ways to make it, 2,000 maneuvers, 18,000 combinations, and that's a single layup to pick up one of the stacking sequences at one location in my structure. So if I'm trying to now optimize the layup to come up with the best layup among all these possibilities, each of those possibilities, the best way to do it is with genetic algorithms. We'll talk about genetic algorithms in the second course, in the next quarter, but I'm sure most of you have heard. What that allows you to do is to evaluate a lot of designs very quickly and find the best ones and use those to generate improved designs until you converge to something that satisfies all the requirements and is the lowest weight, let's say. But to do that, you would need to do a whole bunch of iterations, which ends up being about 15,000 different designs for one case. So all this means you have to do 270 million analyses for an aircraft. If you're trying to do 270 million analysis, you need to do more than 500 per minute if you're working 24 hours a day, 365 days a year, to finish them all in 1 year. So if you are going to do this with finite elements, which is the most accurate method, you will never finish. That's why this course, or courses like this, can be useful. You are not going to get the methods that are the best methods in all cases, but they will be reasonably accurate to give you a quick design which allows you, for example, to do optimization and do these 270 million analyses much faster than using finite elements. In fact, Airbus back in 2009 were saying that within an aerodynamics context, but it's exactly the same story. You can either test everything or you can analyze everything. And they said that running computer models at different altitudes is costly, whereas in a wind tunnel, the model can simply be rotated and the impact measured. So no matter what people tell you, we don't have the computer power and the speed to actually do all these cases accurately enough. And we need to compromise and back off. So the structural design process has a basic objective, which says I'm given a series of requirements, and I will need to come up with a structure that meets those requirements and has certain desirable attributes. And what all this means is, for example, I'm told that you have to fill in, the structure has to fit into this space, because if it goes outside this boundary, then it interferes with something else. And I have some applied loads and applied displacements potentially and hard points that I can use to hold my structure. And after you spend some time doing those millions of iterations, you come up with the best design, which has these lightning holes with reinforcements around them and locations where you can actually apply the loads and react the loads and so on. So that process, going from the blue blurb here to real structure, is partly what this whole course is about. And you have to do that, satisfying, first of all, the basic design requirements, which are the 3 Fs, fit, form, and function. It has to fit there without interference, it has to perform the function, and will have to have the proper shape to actually perform that function. It has to meet the applied loads, and then there are all the other desirable attributes. Should be corrosion resistant, the natural frequencies should be reasonable because we don't want any kind of resonance happening. Thermal expansion coefficient for space applications is a big deal. You want to keep that as low as possible, or at least compatible with between the different parts of your structure so you don't develop thermal stresses. You need to provide attachments for other structure, paths for other structure, and so on. This is the nightmare of any structural engineer. You have this perfectly good design, optimized, and then here comes the systems person and electronics person and says, by the way, there's lines that have to go through hydraulic lines or electrical lines. I need holes there. And you don't have an option, because they always win the argument. And then you have to redesign. We'll talk about some of this more. So the desirable attributes, and we are wrapping it up. Minimum weight, minimum cost, and then you can split this. Recurring, which means every time you make something, you minimize the cost. Non-recurring, which is the associated with the investment that goes once. Basically, the molds that you make to make a part, minimizing that cost, because that can be one of the drivers depending on how you operate as a company, assembly costs, and so on. Low maintenance, replaceability across assemblies. If you, until 10 years ago, you took a part from one aircraft, tried to fit it in the exact same location in the nominally the same aircraft, it wouldn't fit. There would either be a gap or it would be slightly bigger because of tolerances, which we couldn't control well enough with standard touch labor-based processes. Now that everything is becoming more and more automated, we can actually drive those tolerances down, and you can replace across assemblies. Specific natural frequency placement, for example, a helicopter fuselage, if its natural frequency is close to the driving frequency from the blades, not only is it a very unhappy ride for the people in because they vibrate like crazy, it's not a very long ride either because eventually you have failure. Zero coefficient of thermal expansion for space applications, and so on, and you can combine these. We will continue this discussion on Monday.